Okay, thank you very much. The program for this week's lectures will be 4, and conveniently listed as Rocky 1 through Rocky 4. And today will be a review of the universe observed, the observational basis for cosmology, and trying to understand the origin of structure. Tomorrow I will talk about the growth of cosmological structure, both in the linear regime in the early universe and also in the late universe, that we get information mostly from numerical simulations. On Wednesday, in the third lecture, I will talk about inflation, which is our best picture, our best idea for the origin of the perturbations that lead to structure that we observe. And finally, on Thursday, I will talk about dark matter and dark energy, how the matter and energy content of the universe is part of our picture for the origin of structure. So today's lecture, The Universe Observed, will just be a review of cosmological parameters. And including in cosmological parameters are Hubble's constant, the deceleration parameter, as it's traditionally known, but as we shall see, perhaps it should be called the acceleration parameter rather than the deceleration parameter. I will talk about something that I like to refer to as the cosmic food chain. What's important in the universe today in its contribution to omega. So the total density of the universe and the fraction of the density in the universe that's in matter, baryons, possibly a cosmological constant, photons, or neutrinos. I will talk about the age of the universe and the temperature of the universe. And then I would like to introduce a statistical measure of the structure in the universe, the power spectrum of large-scale structure, and something that's similar that's used to analyze the microwave background radiation, the power spectrum. So let me start with a little bit of history of the theoretical developments of the Big Bang theory, starting in 1917 with the work of Einstein. And a couple of years ago, I was driving through the state of Florida, and I saw that bulletin, that billboard, and I didn't know God had to advertise, but who knows. So the idea of the Big Bang model started with Einstein and then developed by de Sitter and sort of classically culminated with the work of Friedman and Lemaitre. And the basic ideas that developed during this time is the idea of the cosmological principle, that the universe is the same everywhere, that the distribution of matter in the universe and radiation in the universe on the largest scales are homogeneous and isotropic. Einstein, of course, did not believe in the expanding universe and stood on his head to avoid finding a solution for the expanding universe. So when I teach cosmology at the University of Chicago, and everyone who teaches cosmology to graduate students starts out the first day writing down Einstein's equations and saying, obviously, the cosmological solution describes either an expanding or a contracting universe. It wasn't so obvious in 1917 to Einstein. But later in the 1920s, Friedman, Lemaitre, Robertson, and Walker developed the metric that describes a homogeneous isotropic universe, the Robertson-Walker metric. And this is the usual way it's written. It could be familiar to some of you, maybe not to all, and we will visit it from time to time. Along with the theoretical developments, there were observational developments in the period of 1912 to 1929. And the observational developments were really the result of the investment by a large number of organizations in the U.S. For the first generation of very large telescopes. This is a picture of the Hooker telescope on Mount Wilson, the 100-inch or 2.5-meter telescope that Hubble used to discover the fact that there are that the galaxies that we see are external to our own galaxy, and he used it to discover the expansion of the universe. It's quite a list of characters in the astronomers who were responsible for these developments, starting with the work of Henrietta Leavitt, who it's not quite fair to call her an astronomer at Harvard University in around 1915 and 1912. She was employed more as a secretary, but she made some amazing insights into Cepheid variables that allowed people to discover the expansion of the universe. The expansion of the universe was actually discovered much before Hubble in the work of Veslo Slipher, who's shown there. Is there a laser pointer? Oh, this is it. Wow. Do you put it on stun or something? Is it? Oh, okay. Okay. All right. This is Slipher. The first discovery of the expansion rate of external galaxies was made by Slipher when looking at the Andromeda galaxy. The reason he was looking at the Andromeda galaxy is he was ordered to look at the Andromeda galaxy by his boss, Percival Lowell, because Lowell was certain that the Andromeda galaxy was only 10 parsec away, and it was not a galaxy, but it was a proto-solar system in the process of forming. And the satellite galaxies around, the irregular galaxies around Andromeda were believed to be planets in the process of forming. And what Lowell wanted to do is to measure the orbital velocity of these proto-planets about the proto-star. And he never did believe the results of Slipher that it had an enormous velocity. The next major discovery in observational astronomy was by someone you probably never heard of. His name was Humason. Milton Humason started working on Mount Wilson in an unusual position. He started working there as a person who drove the mules up the mountain to develop the equipment to Mount Wilson. He never finished high school. He started life as a mule driver. And because he was used to working with stubborn mules, he got along well with the astronomers at Mount Wilson. And he ended up getting a job as a janitor and then started doing observations. And in fact, he was the person who actually discovered Cepheid variables in the Andromeda galaxy. He looked at a plate that was developed by Harlow Shapley and took out a grease pencil on this emulsion plate and circled a star and said, this is a variable star, this is a Cepheid variable in Andromeda. This was the discovery made by Hubble in 1924. It was made by Humason before on Shapley's plate, but Harlow Shapley saw this janitor write on his plate, took out his handkerchief, rubbed off the mark that Humason has made, and said, do not ever write on my plates again. So I guess the moral of this is to pay attention to janitors when they find things on your plates. And of course, the person people are familiar with is Edwin Hubble. And I thought I would say a couple of words about Edwin Hubble because I wrote a book about the history of cosmology. And at the University of Chicago, I looked into some of the archives of Hubble and into some of the letters of recommendation that were written by people at the University of Chicago about Hubble. And it's sort of interesting to look back in the letters of recommendation written in the 1920s. They describe Hubble as physically, he is a splendid specimen, something that I've never seen in a modern letter of recommendation, that he has a magnificent physique, that he's manly, and he is a lovable character. Now, actually, Hubble has something in common with someone who is now well known at CERN, and you can probably guess who this person is. He has something in common with Jack Steinberger. Not necessarily a splendid physique, but the fact that he was an undergraduate and a graduate student at the University of Chicago. And I'd like to point out that Hubble at the University of Chicago was well known as an athlete. There's Hubble there. He was a starting center on the last decent athletic team we've had at the University of Chicago, the 1909 National Championship basketball team. So Hubble may be the only astronomer that I know of to have been a starting center on a national championship basketball team. All right, so much about Hubble. After that, he went and became an astronomer, and he had a night assistant who was fairly well known. And in the period from 1912 to 1929, the validation of the cosmological principle first emerged when Hubble discovered, in fact, that the spiral nebulae were distant galaxies, and the distribution of matter in the universe is isotropic about us. And the discovery in 1929 made by Hubble that was really the evidence for the Big Bang model is the fact that the discovery that the universe expands. And the expansion of the universe, as written by Hubble, is an expression for the recessional velocity of galaxies being proportional to the luminosity distance to the galaxies. So Hubble's law is that the recessional velocity is equal to some constant that's known as Hubble's constant times a measure of distance that's known as the luminosity distance. And I want to go into this in some detail because basically looking at the Hubble diagram is the basis for the present understanding that there may be dark energy in the universe. So let's look at Hubble's discovery paper in 1929. This is the data that was published by Hubble in 1929, and you can see the obvious fact that the distance, that the velocity of the galaxies are perfectly well fit by a linear relationship with distance. Now, there are a couple of things we can say about this paper. When I always show this to my graduate students who are becoming laboratory assistants and will be grading the papers of the students. And as you know, in physics laboratories, no matter what the data look like, people draw straight lines between all the points. And Hubble was guilty of the same thing. And something else I point out, of course, is that he has the units wrong in velocity, but that's not so bad. He gets the units wrong and he draws a straight line. And the conclusion that Hubble drew is that the velocity is a linear relationship with the distance, and the constant, the expansion rate, as determined by Hubble in 1929, was 500 kilometers per second per megaparsec. Of course, now we know that Hubble was right, although this evidence is not really striking. But if we look at the Hubble relationship, the Hubble diagram, the recessional velocity as a function of distance, if we go out to much larger distances than Hubble used, so Hubble's original data were down here, that indeed it is a linear relationship. So let me go into the distance-luminosity relation, the Hubble diagram, because what I want to do is to develop the idea and the understanding of dark energy and the present acceleration of the universe. The present value for the Hubble constant is, there was the Hubble Key Project that just reported their final results, Wendy Friedman et al. They get a result for Hubble's constant in units of 100 kilometers per second per megaparsec of 0.72 plus or minus 0.03 statistical and 0.07 systematic. There is another group who looks at the same data, a group of Sandage Taman, who's in Switzerland, and collaborators look at the same data and get the result of 0.57 for Hubble's constant plus 0.02 statistical, and they do not have any systematic errors. So the usual number that's adopted is either 0.72 or 0.57, and of course with very small error bars that are not overlapping. So how is the distance-luminosity relation determined, and how does it depend upon other cosmological parameters? So what is a luminosity distance? So you say that the distance depends upon the expansion rate, but is it the distance to the galaxy now, the distance to the galaxy when the light was emitted? What exactly do you mean by the distance to the galaxy? Well, what you mean by the distance to the galaxy is the luminosity distance. So what you actually measure in the laboratory, with the telescope, is the flux, the energy flux, the energy per unit area per unit time. And what you're going to pretend in astronomy is that you know the intrinsic luminosity of the object. So the usual inverse square law is that the flux is the luminosity over 4 pi times some distance squared, and it is this distance that is defined as the luminosity distance. So again, the flux is something that you measure, and the luminosity is something we're going to pretend we know. Now, the relationship between the luminosity distance and the redshift can be derived with the help of the dynamical equations describing the expansion of the universe. And essentially, this luminosity distance is determined by conservation of energy. And there's a couple of factors that enter there. The first factor is that the flux is redshifted by a factor of 1 plus z squared. One of these factors of 1 plus z is a redshift of the energy. So the energy of the photon as it travels between the time of emission and the time of observation is redshifted by a factor of 1 plus z. There is also an additional factor of 1 plus z that results just from the time dilation, the fact that a time interval during the emission of the radiation is stretched by the expansion of the universe. So this leads to an additional factor of 1 plus z. Now the flux is the luminosity divided by the area of a two-sphere centered on the source at the time of detection. And this area can be determined by the Robertson-Walker metric, and it depends upon the expansion of the universe. So the Robertson-Walker metric is written in the form that we wrote before, and this would tell you that the area of a two-sphere is 4 pi a squared times r squared. So the relation between the flux and the luminosity, which determines the luminosity distance is the scale factor today, the scale factor describing the expansion of the universe, times the co-moving coordinate of the source times 1 plus z. So light from a co-moving coordinate r reaches us now redshifted by an amount 1 plus z. And all these transparencies will be on the web, so you don't have to worry about the individual details. So what we want to do now is to relate the scale factor times r to the redshift. And we do that from the solution of the field equations describing the expansion of the universe. So if we know the metric, the Robertson-Walker metric, then putting that into the Einstein equation gives us the Friedmann equation for the expansion rate. H is the expansion rate of the universe. The present value of the expansion rate is the Hubble constant. So the expansion rate of the universe has a curvature term, and it depends upon the energy density rho. Another equation that can be obtained from the Einstein equations is an equation for the acceleration, a double dot. And a double dot depends upon the energy density plus 3 times the pressure. And astronomers define a deceleration parameter, which is the dimensionless measure of the deceleration. So it's a double dot over a, and it's normalized by 1 over 8 squared. So the expansion rate is a measure of the increase in a dot, the velocity of expansion. And the deceleration parameter is a measure of how the velocity is changing, is the acceleration. To find the evolution of the scale factor with time, it depends upon the energy density of the universe. And in general, there are several components to the energy density of the universe. There's a matter energy density, a radiation energy density, a possible cosmological constant, and possibly other terms. From conservation of energy, if the pressure is related to the energy density by some constant W, so W is equal to the pressure divided by the energy density, then the energy density in this component changes with redshift as 1 plus Z to the 3 times 1 plus W. So familiar examples of this would be a matter component to the energy density. A matter component is a component to the energy density where the mass is much larger than the kinetic energy. So the effective pressure is 0. If the pressure is 0, then the parameter W for matter is 0. And the energy density for matter scales as 1 plus Z cubed. So the universe at redshift Z had a larger matter density by 1 plus Z cubed. So the matter density just goes down as the volume in expansion. There's a radiation component to the universe. The equation of state for radiation relates the pressure to the energy density, that the pressure is 1/3 the energy density. So W is equal to 1/3. If W is equal to 1/3, the radiation energy density scales in expansion as 1 plus Z to the 4th. If there is a vacuum energy or a cosmological constant, the equation of state for vacuum energy is that the pressure is equal to the negative of the energy density. So W is equal to -1, and if W is equal to -1, the energy density in a cosmological constant is constant, right? It's a cosmological constant. So we can use these facts to solve for the distance-luminosity relation. This is the distance-luminosity relation, and we have to solve for A times R. And we can do that just from the metric. So light travels on geodesics, ds squared equal to 0. So we can use that result to find an integral expression for R related to the expansion rate as a function of scale factor or redshift. So the expansion rate as a function of Z is the expansion rate today, and it changes depending upon the contribution of the total energy density of the universe, the matter energy density, and whatever terms you might have. So these parameters omega are defined in terms of the energy density divided by the critical density of 3h0 squared over 8 pi g. The total value of omega is the matter plus lambda plus radiation plus whatever you have. So there is an integral expression that you can find that can be integrated to give R, which is needed in the distance-luminosity relation, and the redshift Z. And it depends upon omega, omega matter, and whatever you have in the universe today. Okay, so this is the same expression written again. We're interested in the luminosity distance relation, and we can solve for A0 times R by doing this simple evaluation. So the program is to measure the luminosity distance by measuring the flux as a function of redshift of objects for which you know the luminosity, the intrinsic luminosity. Then we can input various values for omega sub I and calculate A of T0 times R and find the distance redshift relationship. Now, all of the expressions for small z just recover Hubble's law. But the order z squared corrections depend upon the various contributions to omega sub I. So there's a simple example that we can study. That's to assume that today the only contributions to omega are matter, a matter term, plus lambda. So there are two parameters, omega matter and omega lambda, and let's go and the omega 0 is omega matter plus omega lambda. So there will be only two parameters, and we can compare the results of this to observation. The first thing we need to do this program are objects for which we know the luminosity. We need standard candles, and it's believed that the standard candles are provided by type 1a supernovae. Type 1a supernovae are exploding degenerate stars that do not have an atmosphere, and the intrinsic luminosity divided by the solar luminosity of these objects are believed to be calibrated, and these different colors correspond to different supernovae. So there's a certain light curve that the supernovae follow, and if you measure a supernova light curve, you can determine the peak luminosity and use that as a standard candle. And this program has been done by two groups. This is the result of the supernova cosmology project of Perlmutter et al. There is also another team known as the High Z supernova team, and they have similar results. So what they do is to measure the apparent magnitude of the object and as a function of the redshift. And these are low redshift supernovae, and these are the high redshift supernovae. So this is a flux redshift measurement, and going back, what we're doing is using supernovae for L, measuring the flux, and determining the luminosity relationship. And the parameters that enter, again, are omega matter plus omega lambda. And these are the theoretical curves that result from those equations for different choices of omega matter and omega lambda. So this top curve is omega matter equal to 0, omega lambda equal to 1, omega matter equal to 1/2, omega lambda equal to 1/2, omega matter equal to 1 with no cosmological constant, omega matter equal to 0.5, omega lambda equal minus 0.5. So there would be different Hubble diagrams for different choices of the cosmological parameters. And using this, you can do a statistical analysis and see what fits the data and what doesn't. Now, the surprising result is that the results are not at this point, which is the point of maximum theoretical bliss. This is the beautiful universe that everyone wants to live in. It is a flat universe with omega matter equal to 1, and it has 0 vacuum energy. Any reasonable universe would be here. The data, however, are many sigma away from this point. The data suggests a universe that has some combination of vacuum energy plus matter. So the data find, rather than a deceleration of the universe, an acceleration of the universe caused by a positive value of the vacuum energy. So the two parameters are omega m plus omega vacuum, and this is the error ellipse from these observations. This is some future result that they hope for if they have a satellite, but this blue area is the result now at different confidence levels. You see it is many sigma away from the point of maximum theoretical bliss. This is the evidence that there is a cosmological constant or some changing non-zero vacuum energy, or something that people don't like to talk about, some unknown systematic effect. So this is evidence that the universe is accelerating. Now, how can we understand that the vacuum energy causes an acceleration of the universe? Well, if we look at the usual Newtonian result for the acceleration of the universe, the second derivative of the scale factor, we would expect that the acceleration is minus, because gravity is attractive, g times rho. So this would result in the familiar curve of the evolution of the scale factor with time, where the universe starts with a bang about 15 billion years ago last Tuesday, and then expands and slows in expansion because of the attractive nature of gravity. So it slows and either slows and eventually recollapses or expands forever. However, that's not, as we saw, the complete expression. There is a relativistic correction to this classical equation, to the Newtonian result, that involves the pressure. So it's not just g times rho, but g times rho plus 3p. And you can think of the pressure term as arising from the kinetic energy density. And it's not only the rest mass energy that gravitates, but also the kinetic energy density. So the universe will decelerate, have the normal expression, the normal behavior, only if rho plus 3p is positive. An indication of an acceleration of the universe, where a double dot is positive, results if the energy density plus 3 times the pressure is negative. And the pressure of minus the energy density is the equation of state for vacuum energy. So if there's an accelerated phase in the expansion, it's evidence that rho plus 3p is negative, and one possibility is a cosmological constant. So the universe seems to be accelerating today. That's what the observations suggest. Normal matter slows the expansion rate and would lead to a deceleration because gravity is attractive. It is negative pressure caused by the cosmological constant that would cause the acceleration and push space apart. So the vacuum energy, the mass energy density of space, is positive, but its pressure is negative. So the evidence from the Hubble diagram that the universe is accelerating is evidence that there is vacuum energy in the universe. Now, this is such an important result that it requires some other evidence than just the Hubble diagram. So I'd like to talk about the case for lambda today, the case for a vacuum energy in the universe today. The first piece of evidence that we see is the acceleration of the universe as measured here. So the Hubble diagram is not fit by just matter energy density. It requires a component with an equation of state that leads to acceleration. There is also evidence for a cosmological constant, or a vacuum energy, from observations of large-scale structure. Tomorrow we will see how to calculate the transfer function, but these are model universes for the power spectrum of large-scale structure, and it depends upon, this is the data from the 2DF data, and this is well fit by a model universe that has a combination of omega in matter times h of 0.2. This would be a model with omega in matter times h of 0.4, and this is a model with omega times h of 0.1. So the evidence for large-scale structure suggests that the product of omega in matter times h is 0.25 plus or minus 0.05. So if omega times h is 0.25 and omega in matter is 1, that says that the Hubble constant is only 25 kilometers per second per megaparsec. Only even half the value that even Sandage derives. If omega in matter times h is 0.25 and h is 0.7, the results of the Hubble Key project, then omega in matter is 0.35. So this is evidence that omega in matter is 0.35 and not 1. There is also evidence, indirect evidence, for a cosmological constant by determinations of the age of the universe. The age of the universe is estimated by looking at the cooling of white dwarfs White dwarfs are old objects that cool slowly. By measuring the present temperature distribution of white dwarfs in our galaxy, we can estimate how long ago white dwarfs started cooling. It's also determined by nucleocosmochronology, by looking at the abundance of elements, and by globular cluster evolution. In the past year or so, there's been some advances in nucleocosmochronology and globular cluster evolution. What we've had in the last year is the first measurement of uranium in a star. So nucleocosmochronology looks at abundances of radioactive elements and uses the relative abundance of isotopes to estimate the age of the universe. Until the last year, what we had to do is to wait for something to fall on our head, wait for a meteorite, and look at the isotopic abundances in the meteorite. But in the past year, it's been possible to make the first measurement of stellar uranium in a star, and that results in an estimate for the age of the universe of 12.6 plus or minus 3 billion years. There's been some recent advances in fitting globular cluster evolution, and this results in an age of the universe of 13.5, an estimate for the age of the universe of 13.5 plus or minus 2 gigayears. So the idea is that the universe is older than the oldest elements and older than globular clusters. So this is the recent results for nucleocosmochronology and globular cluster evolution. If the Hubble constant is 70, and the universe has no vacuum energy, but is flat, then the age of the universe is predicted to be 9.3 gigayears, which is small, uncomfortably small, compared to the estimates from the age of the universe. If the universe is open, has a total value of omega of 0.3 with a zero cosmological constant, then the universe would be older, would have an age of 12 gigayears. And if it's even more open, if omega decreases, then the expansion age of the universe decreases also. If the universe has a cosmological constant, however, the universe will be older for a given value of omega matter. So if omega matter is 0.3 and omega lambda is 0.7, the age of the universe would be 13.5 gigayear. And if omega matter is 0.2 and omega lambda is 0.8, the age of the universe would be 15 gigayears. So in order to have a universe that's comfortably old enough, it suggests that there should be a cosmological constant. The final piece of evidence for a cosmological constant is exercise from arithmetic, and it goes to the result of 1 minus 0.3 is 0.7. And this is due to the result that there is observational evidence from the microwave background radiation that the total value of omega is equal to 1. And this comes from looking at the spectrum of the fluctuations in the microwave background radiation as a function of the multipole moment. If omega is equal to 1, there is a peak at L of about 200. If omega is equal to 0.3, then the peak is at L of about 300 or 400. Determinations of the peak suggest that the total value of omega is 1.03 plus or minus 0.06. So the total value of omega today is equal to 1, and we don't see that in any form of matter. Recent determinations of the baryon fraction of the universe is much smaller than 1. People measure the baryon fraction by looking at the absorption of light from quasars by Lyman alpha clouds. So here's a typical astronomer looking at a quasar, and the light from the quasar passes through a cloud, and there's absorption. And if you look at the absorption, you can determine a feature due to deuterium. You see that striking feature right there? That's due to deuterium. And this is Lyman alpha absorption from the hydrogen. So it's possible to measure the deuterium abundance at very high redshift before there was a lot of stellar evolution. And the determination of the deuterium abundance is here, and this is the prediction from Big Bang nucleosynthesis for the deuterium abundance as a function of the baryon density. So by measuring the deuterium abundance and comparing it to the prediction of Big Bang nucleosynthesis, we determined that omega in baryons is much smaller. Not only is it much smaller than 1, but it's much smaller than the total mass density, which from galaxy kinematics, X-ray gas, and lensing is fit by omega of matter of about 0.3. So we have the following problem. The total mass density of the universe in these units is 1. Omega in matter seems to be 0.3. That leaves a cosmic deficit of 0.7. And this cosmic deficit of 0.7 is easily fit conveniently by a cosmological constant of 0.7 as suggested by the supernova observations. So that is the direct and indirect evidence for a present energy density of the universe. So if this is correct, then there is a mass density of space of 10 to the minus 30 grams per cubic centimeter. That's a fundamental mass density of space. And it's, I think, better described as a cosmo-illogical constant because it's such an incredibly small value compared to any other scale in physics. And the question is, who ordered that? Where does that come from? How does one understand the unbearable lightness of nothing? Another cosmological parameter is the present temperature of the universe, and that is very well determined by the Cosmic Background Explorer satellite. And this satellite measured the spectrum of the radiation of the black body spectrum, and this is the results of their experiment, and the error bars here have been blown up by a factor of 100. Because if I would plot them in the regular units, of course, it would be so much smaller than the thickness of the line, you would not be able to see them. So the best black body in the universe is the universe. It's exquisitely well fit by a black body of 2.726 degrees Kelvin. So the temperature of the universe is well known, and if we know the temperature of the universe, then we know the energy density of the universe in radiation. So let me summarize the cosmic food chain and the contribution of radiation, visible matter, neutrinos, dark neutrons and protons, dark matter and dark energy in terms of omega. Radiation is not a very large component. It's only about 0.02%. Visible matter, the stars and things that are shining at us, is only about 0.1% of the critical density. If neutrinos have a mass of a few times 10 to the minus 2 electron volts, as suggested by atmospheric neutrino oscillations, then neutrinos have as large a mass density in the universe as visible matter. Most of the neutrons and protons in the universe are dark, contributing about 10% to omega. Dark matter is about 30%, and dark energy is about 60%. Now, it used to be said that the universe is so exquisitely, beautifully put together that it's evidence for intelligent design. Now, I'd like someone to explain the intelligent design in this distribution of the various components of the universe. This does not look like the universe that would appear on the resume of a supreme being, right? It just doesn't make sense. Okay, so that's the story with cosmological parameters, and in the last 5 minutes, yes, it will be 5 minutes, let me turn to the power spectrum of the distribution of matter and the power spectrum of fluctuations in the temperature. First, let me remind you of the observer's view of the universe, that the universe, the distribution of matter is inhomogeneous and isotropic, that the universe is full of interesting things to look at, stars, galaxies, clusters, etc. This is the observer's view of the universe, which can be contrasted to the universe as described by a theorist. So to a theorist, the universe obeys the cosmological principle. The universe is homogeneous and isotropic. It's completely smooth. So which point of view is correct? Well, we can quantify the question, is there structure in the universe? How much structure? Is it homogeneous or not? By constructing something known as the power spectrum. So we're going to assume that there is an average density to the universe, rho bar, and expand the density contrast, the density field of the universe, the density as a function of spatial position, minus the average divided by the average. We're going to expand that in Fourier modes. Now, if we form the autocorrelation function, the two-point correlation function of the density field, then it depends upon an integral over wave number of delta of k squared. Written in this way, the power spectrum, k cubed delta of k squared over 2 pi squared, is the amplitude per logarithmic interval in k of the fluctuations. So if this is large for a given value of k, it means that for that value of k, there is a lot of structure in the universe. So this is the power spectrum, or sometimes the power spectrum is just described as delta of k squared. So the power spectrum is related to the RMS fluctuations. So the power spectrum on some scale r is approximately equal to delta at k at a wave number of r to the minus 1. And I'll let you put in the 2 pi's wherever you want. So how would one measure the power spectrum? So let's say you look through a telescope and you see a distribution of galaxies or a distribution of matter that looks like this. Well, it's a simple procedure. You can, on this little piece of paper, imagine that you have a sphere of radius r and put it down at some random place in the sample. So this would be trial 1, and you would count the number of galaxies or the number of objects within this circle. Then you put it down some other place, and you count a different number of galaxies in this circle, because that is not exactly a homogeneous and isotropic distribution. You do it again, and you do it as many times as you can make your graduate student do it, right? So you make your graduate student do it many times, and you can find the average number of galaxies that's contained in a sphere of radius r. And if you know the average, you can calculate the variance. And if you know the variance, then you know the power spectrum at a wave number of r to the minus 1. So your graduate student comes back exhausted, saying, I've done this calculation. And then you say, great, now take a different value of the radius, and then go through the procedure again, and eventually you can find the power spectrum. The power spectrum is emerging now from studies of large-scale structure. There is an Anglo-Australian collaboration, 2DF, and they measure the power spectrum. And they find that the variance, the RMS variance, becomes larger than unity at a distance scale of about 8 h to the minus 1 megaparsec. So on scales larger than this, the distribution of matter is smooth, and on scales smaller than that, it is lumpy. There is another experiment going on, the Sloan Digital Sky Survey, which will extend information of the power spectrum to smaller value of k larger values of the length scale. So that's the power spectrum in matter, and now we can turn to the power spectrum in radiation. So if you ask an observer to describe the radiation in the universe, this is a pattern of microwave fluctuations as seen from Chicago. And there are hot spots and cold spots, and the observer would say that the temperature of the universe is not uniform, but of course the theorist's view of the universe is that the temperature is isotropic. Again, one can quantify this by forming an angular correlation function, which is the temperature correlation function. But rather than expand in Fourier modes, because the sky is a two-sphere about us, it's convenient to expand the temperature correlation function in spherical harmonics. And the amplitude in in multipole number L is known as C sub L, and C sub L as a function of L is the angular power spectrum of the microwave fluctuations. In the last century, in the 20th century, if I would show you a graph of determinations of the angular power spectrum, C sub L as a function of L, the graph would look like this, and you don't see very much information there. But in the last couple of years, there have been 3 experiments that have measured the angular correlation function, C sub L as a function of L, and have shown the peak that determines a value of omega 0 of 1. And as a theorist, I see 3 additional peaks there. And we'll see what happens, because we will soon have more information, because there is a satellite known as MAP that's at the second Lagrange point right now taking data. And the expected precision of MAP is shown by this yellow band, and in this region it's smaller than the thickness of the line. So we'll soon have exquisite data within the next year or 2 on the microwave background fluctuations angular power spectrum. Okay, so in this first lecture I've spoken about Hubble's constant and evidence for the deceleration of the universe. I've talked about the present universe, the cosmic food chain, values of omega 0, omega matter, omega baryon, etc. I've talked about evidence for the age of the universe and the temperature of the universe, and have introduced the concept of the power spectrum for large-scale structure and the anisotropy in the microwave background radiation. And tomorrow I will talk about the growth of cosmological structure, how to start with the universe that is roughly homogeneous and isotropic, and grow galaxies and large-scale structure. Thank you.